Previously, we have related the Pauli x, y, and z operator to rotations of 180 degrees around the x, y, and z axis respectively. Using spectral decomposition, we also learned how to work out rotations of 90 degrees. In this lecture, we are going to study rotations by an arbitrary angle. Alright, I have summarized the rotation by pi and pi over 2 around each of the axes here for your easy reference. To motivate the discussion of a rotation by an arbitrary angle, let me first ask the question, what is the rotation by a 45 degree, that is pi over 4? Well, we can just simply repeat the argument because a rotation of 90 degrees is made up of two rotations of 45 degrees, and hence this rotation must be the square root of the square root of x, and similarly for the y and similarly for the z. To find them, we simply use the spectral decomposition again. Here, I will just illustrate this method using the rotation around the z-axis, since you already know how to do the computation with the other axis. For the rotation around the z-axis, the matrix representations are particularly easy because we are using the computational basis, which is the eigenbasis of the z operator. Hence, the rotation by 45 degrees is simply the square root of the S matrix. Here, we need the square root of the eigenvalues 1 and I. So, by choosing the convention, square root of 1 is still 1, and square root of I is e to the power of I pi over 4. This is simply because I could be written as e to the power of I pi over 2. Hence, the square root of I is simply e to the power of I pi over 4. So, the matrix representation for the square root of the S matrix is simply 1, 0, 0, and the square root of I, which we take as e to the power of I pi over 4. By convention, we normally factorize out a global phase of e to the power of I pi over 8 and write this matrix in a more symmetrical form, with the two diagonal elements being minus I pi over 8 and e to the power of I pi over 8, with zeros on the off-diagonal elements. And this gate actually has a name, it's called the T gate, or the pi over 8 phase gate, as suggestive from the diagonal elements of this two phase. So this T gate represents a rotation of 45 degrees around the z-axis. Similarly, you could work out the rotation of 45 degrees around the x-axis and around the y-axis, and these are left as homework for the readers to find out. Equipped with this general recipe and the whole structure of finding the function of an operator, we are now ready to find the matrix representation of a rotation by an arbitrary angle around any of the axes. To illustrate this, I will again pick the z component. For example, if I would like to rotate around the z-axis by an angle of delta, this delta is arbitrary, what is the rotation matrix for that? Well, as the argument goes, we can think of the pi rotation as 2 pi over 2 rotations, or 4 pi over 4 rotations, and so on and so forth. So let's just assume that pi is a multiple of delta first. Later, we will see that such assumptions can actually be lifted. So for now, let us rewrite n as pi over delta. This is to say that in order to realize a rotation of 180 degrees, we can actually do n consecutive rotations, where each time we are rotating by delta degrees, where n is equals to the pi over delta. Hence, to find the matrix representation for the rotation by an arbitrary angle delta, we need the nth root of this matrix Z. So for that, let us remind ourselves again that Z is already diagonal in this eigenbasis, with the two eigenvalues 1 and minus 1. So for its nth root, we need the nth root of 1 and nth root of minus 1. By convention, we take the nth root of 1 to be still 1, and for the minus 1, since we can rewrite minus 1 as e to the power of I pi. So the nth root of -1 will be e to the power of I pi to the power of n minus 1, which is e to the power of I pi over n. Substituting n equals to pi over delta here, this gives us e to the power of I delta. So this is the other term over here. We have e to the power of I delta with the projector onto the 1 eigenstate. So in terms of matrix representation, this could be written as 1, 0, 0, e to the power of I delta. And normally we factorize out a global factor of e to the power of I delta over 2 and be left with e to the power of minus I delta over 2, 0, 0, and e to the power of I of delta over 2, where this matrix is what we will define as the rotation around the z-axis by an arbitrary angle delta. And by now, this global phase factor should not bother you at all. For the rotations around the x-axis and the y-axis by an arbitrary angle delta, you just follow the same recipe, keeping in mind that the x operator and the y operator are diagonal in the plus-minus basis and the plus-minus I basis. So this will be left as an exercise for the readers. Okay, we have worked out the matrix representation of the rotation around the z-axis by an arbitrary angle delta, which is represented as this matrix. Similarly, by using the spectral decomposition, we can also work out the rotation around the x and the y-axis by an arbitrary angle delta, which I will reproduce here as these two matrices for your reference. In fact, there is another way, perhaps a little bit easier. If you are familiar that the x, y, z operators are the generators of rotation around the x, y, and the z axis respectively, that is to say, the Pauli operators, when they are exponentiated, they give rise to the rotation matrices. So here, as an example, the rotation around the z-axis by an arbitrary angle delta can also be defined as the exponential of the z operator by this phase. Let's work this out and to convince ourselves that they are indeed the same. Making use of the spectral decomposition one more time, where we know that the function of the operator is defined on the function of its eigenvalues in its eigenbasis. So here, the z operator is diagonal in the 0, 1 basis. That means e to the power of minus I delta over 2z is simply, the first eigenvalue is 1, corresponds to the 0 projector, so that with eigenvalue e to the power of minus I delta over 2. The second eigenvalue for the 1 cat bra is minus 1. So here we have e to the power of negative I delta over 2 times negative 1. So that is e to the power of I delta over 2. And we can see that this is simply e to the power of I delta over 2 and e to the power of, here is minus, here is plus, 0 and 0. Just exactly the same as how we arrived as the matrix representation for rotation around the z-axis by an arbitrary angle delta before. So as an exercise, you should convince yourself that e to the power of minus I delta over 2x will generate the rotation around the x-axis by an arbitrary angle delta, and e to the power of minus I delta over 2y will generate the rotation around the y-axis by an angle delta. In fact, there is also another way to work out the exponential of the operator z, because I would like to introduce you to a quite important identity. That is, for an operator a which satisfies the property a squared equals to the identity, and with the x being a real parameter, e to the power of ixa is equals to cosine of x times the identity plus I sine x times the operator a. You can verify this identity using the Taylor expansion on both sides of this equation. Equipped with this identity, let me verify one more time that the rotation operator around the z-axis by an angle delta takes this form. So for that, we have e to the power of minus I delta over 2 of the z operator. Instead of using the spectral decomposition as we did before, let me use this identity. So the operator z definitely satisfies the property z squared equals to the identity. So here I will have cosine of the parameter delta over 2. So this negative delta over 2, but cosine is an even function. So this is the same as cosine of delta over 2 times the identity matrix, which is 1, 0, 0, 1. And with the identity here, we also have the second term, which is I sine x, the operator a. So here my x is negative delta over 2. So sine of negative delta over 2, that's negative of sine delta over 2 with this I. So I have minus I sine of delta over 2 with the z operator, which is 1, 0, 0, minus 1. So here you see that for the first entry, I have cosine of delta over 2 minus I of sine delta over 2. That, when written in the Euler form, is just e to the power of negative I delta over 2. Here we have 0, 0. And for the last entry over here, we have cosine of delta over 2 minus, so it's plus I sine delta over 2. So that is e to the power of I of delta over 2. And it is exactly the same as how we wrote the rotation matrix around the z-axis by an angle of delta. So as a homework exercise, I invite you to use this identity and to find out the exponential of the x operator and the y operator with the parameter given by here, and to verify that this gives you the same matrix that is written down over here. Finally, to conclude this part, we've so far studied the rotations around the x, y, and z axis. How about the rotation operator for the rotation about an arbitrary direction specified by the unit vector e? We remind ourselves that in this case, we need to replace the Pauli operator in the x, y, z direction by a Pauli operator that is pointing in this direction e, which is given by e dot sigma. And following the recipe, the rotation operator is given by the exponential of such Pauli operators. Here we have e to the power of minus I delta over 2 e dot sigma. Let's remember that to specify the unit vector e, we need two parameters, the polar angle and the azimuthal angle. In order to specify the angle of rotation, we need to specify the third parameter, which is the delta. This must be the most general rotation that we can do on the qubit. This is because that the rotation axis, E, is arbitrary, specified by theta and phi, and the angle of rotation is also arbitrary, specified by the angle delta. Hence, the most general unitary operation that we can perform on a single qubit must be the form U, which is parametrized using the three parameters theta, phi, and delta, with an irrelevant global phase vector e to the power of I alpha in front, and this rotation around a general arbitrary axis E and by an angle delta. Now, an important remark is in order. It seems quite challenging to do quantum computation because we need to be able to realize rotations around all possible arbitrary directions. However, just as we have seen that many consecutive rotations can compose into a single rotation, it is also possible to do the reverse. That is, a single rotation that is arbitrary around an arbitrary axis by an arbitrary angle delta can also be decomposed as many rotations. And such decompositions are actually not unique. There is an important theorem called the ZY decomposition theorem, which says it is possible to decompose a general unitary operation acting on a single qubit as rotations around the z and y axis only. So in particular, this unitary operator can always be decomposed as rotations around the z-axis, the y-axis, and the z-axis by an angle of theta 1 first around the z-axis, angle of theta 2 around the y-axis, and another angle theta 2 around the z-axis, with a global phase vector in front. So here we have 4 parameters, and here we also have 4 parameters. It is left as an exercise for the readers to verify that these two expressions for the unitary operators are actually equivalent. Hence, in the Qubit circuit model, if I have a most general U acting on a qubit, this is actually the same as carrying out a first rotation around the z-axis by a certain angle θ1, followed by a rotation around the y-axis by a certain angle θ2, and finally a rotation around the z-axis again by an angle θ3. From the next lecture onwards, we will often switch to the circuit representation of the operators rather than using the matrix representations, and we will use them to study quantum circuit.